Welcome to Saitechinfo channel, my dear students. Today we'll be discussing the moving charges. It is in physics class 12. Moving charges. Charges we already know. This can be represented by Q, is it not? So Q is equal to the integral multiples of electronic charge. And E is the charge of electron in coulombs, N is an integer, and Q, so it is equal to the integral multiples of electronic charges. We know the meaning of current. Current is running, moving, unidirectional movement of, in this case, current electricity. So being current electricity, that is, it is the movement of, unidirectional movement of electrons. Okay. Therefore, the current is indicated in the opposite direction. Okay. So, now, first of all, we should know some of the basic aspects about this moving charges. Lorentz force. You please note down in this lecture, the vectors are indicated in bold letters in your book, but we can indicate by putting an arrow. For instance, if F is the force, then it can be represented as F vector, okay, force vector, right. Now, what is Lorentz force? The Lorentz force is the total charge, the total force on the charge Q. So, as we already discussed, the charge is going to move from one place to another place. So, the total force on such charge Q moving, if any body is moving, it should have certain velocity, is it not? So, this can be represented as V vector because it has got the velocity. So, what is the velocity of electron here? It is V vector, okay. So, the total charge on Q, so Q is the charge, you know the unit of charge is coulomb, okay. Now, so the movement of the charge with a velocity V when in presence of magnetic and electric field. So the magnetic field here, it is represented as B vector, and electric field is represented as E vector. So in the presence of the magnetic field and the electric field, the charge is moving with certain velocity. So if there is any movement under these influences, two influences, what are these two influences? One is magnetic field, another is electric field. So in their presence, the charge is moving in a direction, okay, with certain velocity. Now it is given by F is equal to that is force vector is equal to Q into V, the velocity, is it not? So the V into, that is B plus E, B vector plus E vector, the total field, okay, total field. So this is a kind of what? The total field, and that is subjected to what? A cross product with this. So Q of V cross B, okay, that is normal to the velocity, and the work done by it is 0. So this magnetic force, listen, this magnetic force Q into V cross B, that is normal to the velocity, and therefore the work done is 0. We already know what do you mean by work done. Work done is equal to force into some displacement, is it not? And if it is represented by vector, you can put being a scalar product F dot S. So we can further expand it. When it is acting normally, no work is done, and that is why magnetic force, that is Q, of V in cross V is normal to V, and then the work done is 0. So what is Lorentz force? Lorentz force is expressed as the product of Q and V cross B plus E. Okay, V cross B plus E. Whereas we are just identifying the magnetic force as what? Q into V cross B. That is when it is a normal to the velocity, then the work done is 0. Okay, right. The force experienced by the straight conductor. Let me consider a conductor. It's a straight conductor. Now F is the force. So force being the vector, you can mention F as force. So force vector, whereas L is the length of the vector. Length of the vector, not vector, conductor, length of the conductor. You know, the modulus of the length vector is equal to the magnitude, is it not? The modulus of I, this is modulus of I, that is equal to I, that is magnitude. Now, F is given by, listen to me carefully, F is given by L into vector I cross vector B. What is vector I? That is the current vector. Please note down what is that? This is the current vector. And what about the B? B vector is the magnetic field vector. L, the length of the conductor. And I, that is the magnitude of the current. So modulus of the current vector is equal to I, that is the magnitude. So this equation is very important to explain the force experienced by the straight conductor of length L, and its force is F and the current is I. Now let us move to the next one. The magnetic field around a straight conductor. So let us consider this conductor. The magnitude, the magnetic field around a straight conductor. So this is the straight conductor. Carrying current I. So current is passed through this. Okay. So what could be the magnetic field? So it would be perpendicular. Okay. Perpendicular. Current inwards, that is a B, is clockwise around, it is the clockwise around the straight conductor. Now this is the top view of the conductor. Okay, so when you look at from here, okay, this is our eye. When you look from here, so that is the view. So this view is the top view. Okay, now the clockwise, now the B is a clockwise, current is inward, means B clockwise. Now the current is outward. When a current is going inside, the direction of magnetic field is in the clockwise direction. Whereas when the current is flowing outward, coming out, then it will be in the anti-clockwise direction. Okay, so are you able to visualize this? Right. Let us talk about this Maxwell's right hand corkscrew rule. It is said, if a right-handed corkscrew, is rotated to advance along the direction of the current through a conductor, then the direction of rotation of screw gives the direction of magnetic lines of force. Assuming that is your, let me say some carpenter is working on a table. Now he is driving with the screwdriver. Okay, so what will he do? He will rotate like this in a clockwise manner so that it comes down. So current goes inward. Do you understand? So that is called corkscrew rule. Okay, assuming that. So this is the screw pattern. So when it, and there will be a wedge like this. So using the screwdriver, we rotate to put inside, to keep inside, to insert it, to keep the screw down, that is inward. So when it is going inward, the rotation, we'll be rotating the driver in the clockwise direction, screwdriver in the clockwise direction. That indicates the magnetic field. Do you understand now? So that is why it's called Maxwell's right hand corkscrew. When you unscrew, what will happen? It will come out. So in that case, we'll be unscrewing it. It means that is, it will come out from the, that is a punched bench or anywhere. So we will unscrew, and we have to do the anti-clockwise direction. You have to drive the screw, okay, so that it will come out. So when it comes out, then it is in the anti-clockwise direction. That is, the magnetic field will be in this way. Now the magnetic field due to the circular loop carrying current. Suppose, sir, we were talking about, that is, a conductor passing through this, whether it goes, the current goes in this way or in this way, okay. Now, so when it comes down, it rotates in this way, that is, in a circular pattern, the magnetic field is created in the clockwise direction. So when it comes upward, then it is in the anti-clockwise direction. But when it goes like this, like in the form of loop, what will happen? Because here, what happens here, the current goes inside, it goes here like this, okay. Now it comes here and down. So what happens here, when it goes out from the, when it goes up in this direction only, when it goes up outward, what has happened here, that is anti-clockwise direction. Do you understand this? And now the current comes inside, okay. In this case, it adopts clockwise direction. Then what will happen to the middle? You will develop a lot of parallel field lines. So this is the magnetic field due to circular loop carrying current. So when a circular loop is carrying current, how the magnetic field will be creating its pattern. So that's what we are interested to visualize. Now let me move to the next concept, that is Bio-Savart's law. Bio-Savart's law. So the T can be pronounced silent. So Bio-Savart law. The infinitesimally small magnetic field experienced when the current is passed through a conductor, that has to be measured, that has to be determined. How we can do, and that Bio-Savart law, that is very helpful to determine the infinitesimally small magnetic field created here. So this infinitesimally small magnetic field, dB, it is directly proportional to the current. It means when current increases, you can experience more magnetic field, and it is directly proportional to dl. What is dl? That is the smallest element of the length element of the conductor, dl. So, and what is theta? When the theta is, this is the smallest element. Now the angle between, let us consider this is the xy. Let us consider xy is the current carrying conductor. Xy is the current carrying conductor. It goes like this. The current strength. I is given as current strength in ampere. AB is the smallest length element of the conductor. P is the point. So we have already told, when current is passing through this conductor, it creates magnetic field. So when it creates a magnetic field, we have to feel it. We have to experience it. How? By keeping a point P here. So let us consider this smallest area, the smallest length element of the conductor, that is AB, which is represented as a dl, the shortest length. infinitesimally small length element of the conductor. And assuming that that is developing, I mean that is having an angle between what? Between the DL, the smallest DL in here, and the line joining the element P and the DL. This is the current element, okay, and this is the element DL and the point P. Therefore, the angle between the smallest dl and so this is known as theta. Do you understand this? This is theta. You can mention this as theta. And as far as the smallest distance is concerned, even though it is something like a small curve, it adopts a rectilinear linear motion like this. Therefore, this is the direction of what? The smallest length element. So it is indicated, since it is the smallest length element, the current indicated by the smallest length element is di. Do you understand? So what is this? This is dl. What is this? The smallest current extended like this. So this is di. Now, what is r? The distance of the point kept where we are going to experience the magnetic field created by this smallest current. So that is r. So the distance between this O and P. So O is the central element of the AB. Okay. Now, so theta is equal to angle between the element, I mean the DL and the line joining the DL and P. So these wordings are very, very important. Right. Now let me proceed. The magnetic field of the magnetic induction of the element, that is dB, is directly proportional to the current, as I already discussed, and it's directly proportional to the length element. Then it is directly proportional to the sine of theta. We already discussed what is theta. Then it is inversely proportional to the square of the distance between the point and P and the center of the length element, that is R. So that they talk about this R. You understand? This is the distance, right? And that is indicated by dB is proportional to what? IDL. So we have formed these relations as an equation. So dB is directly proportional to IDL sine theta divided by R squared. So which are all the parameters? I is the parameter current strength, DL the length element, sine theta the angle, or the distance between the point and the length element, center of the length element. Now, when we remove the proportionality, you have to introduce the constant, and that is the proportionality constant K. That is given by mu divided by 4 pi. So this mu divided by 4 pi, where mu is permeability of the medium. What is mu? Permeability of the medium. Then, and permeability of the medium can be represented as mu. Permeability through free space means mu naught. Permeability relatively, then it can be called mu r. So this is the relative permeability, and this is permeability through certain medium. And what about this? This is permeability through free space, that is vacuum. Okay, right. So dB is equal to, now we can replace this K by mu divided by 4 pi. So dB is equal to mu divided by 4 pi into IDL sine theta divided by R square. Right? Now, as we have already discussed, mu R is nothing but, what is this mu R? Relative permeability, not permittivity. That is different. That is epsilon. Now we are talking about permeability, mu R. So mu R is given by mu divided by mu naught. And therefore, what is mu? Mu is the permeability of certain medium. Mu naught permeability through free space. What is mu R? Mu R is the relative permeability. Therefore, what is mu? Mu is nothing but you can multiply these two. So mu R into mu naught. Is it not? Now we will incorporate. So mu is equal to mu r into mu naught. Do you understand? So if it is the case, now we can do like this. We already know mu naught is given by, that is 4 pi into 10 power minus 7 Henry per meter. What is that? Mu naught is equal to 4 pi into 10 power minus 7 Henry per meter. Right? Where the relative permeability mu r for air is 1, right? Then, so in air medium, what is that? In air medium, since mu r is equal to 1, so you can put mu naught instead of mu, and that is why I have taken. Otherwise, you can expand once again this equation as dB is equal to mu naught mu r divided by 4 pi, because mu is equal to mu r mu naught, then I dl sin theta, I dl sin theta divided by r squared. Now this r is equal to, what is this? Mu r, mu r is equal to 1. Why? For air it is already given, and therefore mu naught divided by 4 pi, and that is why for air as a medium, that is, this is the equation. Do you understand? Please note down. Now let us represent the same equation in the form of, what is this law? Bio-Savart's law. So Bio-Savart's law is represented in vector form like this. That is dB vector, because magnetic field is a vector. So dB vector is equal to mu naught by 4 pi into I dl vector into r vector divided by r cube. And you can introduce the unit vector, that is r cap, so that it becomes the modulus. So dB is equal to mu naught divided by 4 pi into I dl into r cap divided by r squared. So you can use either of these equations. And the unit of B is Weber meter square, or Tesla. You can simply put Tesla. Okay. So Weber, that is WB. It can be represented as WB, Weber. So Weber per meter square, or Tesla, that is the unit of magnetic field.